share my slides. Okay. So yeah, hopefully everyone can see this. But yeah, thank you so much, Sarah, for the lovely introduction. So yeah, I've been very interested in factor analysis during my PhD, particularly to derive dimensions of psychopathology to investigate individual differences in cognition. So I know Sarah kind of gave a very general overview, but just to give you an idea of what I'll be talking about specifically. So as an introduction, I want to talk to you about, ways that we conceptualize mental illness and the benefits and limitations to the traditional approaches that we have, and how factor analysis can really address a lot of those limitations. With that, I want to talk to you about computational factor modeling, so a very specific type of factor analysis that we can use to derive dimensions of psychopathology. And then we'll move on to the coding workshop. So as Sarah said, the script and data for that has been made available, and I'll be sharing my screen, going through the script with everyone. But if you haven't used OR before and don't have RStudio, totally fine. There is a HTML version of the script as well that you can follow, or you can just follow me on screen, whatever's easiest. And then finally, I just want to round off by giving you examples of insights that we've gained by using computational factor modeling and new methods that we're trying to develop, supervised computational factor modeling that's a more data-driven way of doing factor analysis. So when we think of mental illness, we define mental health disorders in terms of discrete diagnostic categories using this taxonomic approach. So we think of mental health disorders as like standalone conditions that are independent of each other, and that can be diagnosed using established manuals with symptom criteria. For example, someone presents with feelings of sadness and hopelessness and guilt and tiredness and significant impairment and distress due to these symptoms, and they may get a diagnosis of depression. And we assume these disorders are dichotomous in that you either have them or you don't. So we assume that this is kind of the clinical picture. You're healthy, or you might have depression, or you might have anxiety. And the manuals that really have been adopted globally are these two. So the Diagnostic and Statistic Manual of Mental Disorders, so the DSM, which is derived in America and used for research purposes mostly, or then the European equivalent is the ICD. And this approach, in terms of defining disorders in terms of discrete categories, has been hugely beneficial for lots of reasons. It's allowed for a shared language for diagnosis. So it's very helpful for a patient and clinician to know that they're talking about the same issue. It's also very powerful for someone to have a name to their problems. It gives people the insight that their problems are recognized as a legitimate illness. And finally, as well, these disorders have been really important for treatment guidance. So when someone gets a diagnosis of depression, for example, there's a very specific path that will be followed in order to ensure that they're getting the best treatment available, which might be different from the path if you had, say, generalized anxiety or schizophrenia or an eating disorder. So just to give you a bit of history on these manuals, the DSM was first published in 1952 and has gone through lots of iterations and revisions since. So the most recent being published in 2022, based on the consensus of 200 experts. But with this, there's this idea of disorder inflation, where with each iteration of the manual, more and more disorders are being added. So we're going to put a poll question in the chat, but something I wanted to ask you guys is, how many mental health disorders do you think are listed in the DSM? Do you think it's 420, 138, 202, or 86? So yeah, hopefully that poll has come up if people want to answer and submit. Okay, so hopefully you've gotten the opportunity to answer that, but the answer is 202 items are listed in the DSM-5. So yeah, it seems like most people said 138, and then about 1/3 of people also said 202. So yeah, this obviously is a lot of disorders, and it kind of sets the stage for the major limitations of this categorical diagnostic approach. So 202 disorders are listed, and they're all assumed to be independent disorders with arbitrary thresholds for binarization. This basically means that with these disorders, you have to have a certain amount of criteria to meet the diagnosis. The problem with that is that there's lots of people who maybe only have 8 out of the 9 symptoms, are significantly impaired by those symptoms, but don't get the diagnosis. So again, we have lots of like sub-threshold presentations because of this like arbitrary binarization. And again, these disorders are assumed to be independent of each other. So you can see in this image here, you know, we have depression and anxiety as 2 separate disorders. So with that, you would assume that any co-occurrence of these disorders is purely at chance level. So with that being said, what percentage of individuals who meet the diagnosis for one mental health disorder do you think also meet the diagnosis for a second? Is it 5%, 25%, 50%, or 80%? Okay, so it's not chance level, it's actually 50%. So yeah, actually the majority of you did say 50%, but it's important to know that this is really, really high. And this rule of 50% actually applies the whole way down. So 50% of people with one disorder will meet the diagnostic criteria for a second, 50% of people with 2 disorders will meet the diagnostic criteria for a third, 50% of people with 3 for a fourth, and so on. So this is a major issue in terms of like, you know, people suffering lots of different mental health disorders at the same time. And then just the final question I have for you is thinking about specific disorders. If we have major depression, which has 9 symptoms attached to it, how many different mental health profiles do you think qualify for a diagnosis of major depressive disorder? Given those 9 symptoms, do you think it's 122, 227, 945, or 16,400? So anyone who's good at like permutation will probably get this quite quickly. But yeah, you can just answer through the poll. Okay, so the answer is that it actually depends. So if you just take the 9 symptoms, that will give you 227 combinations. But 3 of those symptoms are extreme poles. So you can be not sleeping enough or sleeping too much. You can not be eating enough or eating too much. You can be moving too much or moving too little. And when you consider the extreme poles of these symptoms, it bumps it to 945. And then actually within all of the symptoms, there's lists of subsymptoms. And when you consider all of those subsymptoms, that actually gives you 16,400. So in theory, you could have 16,000 people standing in front of you, all with different combinations of symptoms, but all of them getting a diagnosis of major depressive disorder. So again, this is problematic because it means that we have a lot of heterogeneity within disorders, but we also have homogeneity across disorders. 40% of symptoms in the DSM repeat at least once, and some of them can repeat up to 20 times. So again, we have a clinical picture like this, where we assume that we have our discrete categories, but the reality is so much more complicated than that. And just one other limitation I want to highlight with this is that, we have really low diagnostic reliability. If you go to a clinician and list your symptoms for mood disorders, and then they give you a diagnosis, and then you go to another clinician next door, give him the same list of symptoms, the chance of getting the same diagnosis is actually really low. So yeah, this is a major problem with the way that we conceptualize mental health currently, or mental illness currently. These disorders are a convenient fiction rather than a clinical reality. And this has led to huge issues if we want to identify the neurocomputational mechanisms underlying disorders. If you look at the association between these disorders and like brain structure or brain function or neuro or cognitive behavioral performance, the results are very inconsistent and non-specific. And I think this really speaks to like the overpromise and failure of biomarker research. And we can't seem to figure out what are the mechanisms underlying these disorders. As well as that, it's a major problem for treatment development and allocation. We have general pathways for treatment guidance, but the reality is we don't know what treatments work for whom. People are prescribed treatments based on trial and error and resource availability. And when treatments work, we don't know how they work. So again, all of these are major issues that can be, I think, traced back to the way we just conceptualize mental illness. So this has led to like a real and demonstrable paradigm shift in the way we conceptualize these disorders. So with that, I want to introduce the idea of computational factor modeling. So this is an alternative approach that derives transdiagnostic dimensions of psychopathology and that have precise neurocomputational mechanisms. So rather than looking at disorders in patient samples, what this approach does is it gets data from really large unselected samples of people who endorse a wide range of mental health symptoms, and looks at the co-occurrence of those symptoms in these populations. So like for robust exploration and generation of these factors. So you would get a really large sample of people to complete a battery of questionnaires, say relating to anxiety and OCD and schizotypy and depression. And then you construct a correlation matrix of their item level responses. And this correlation matrix will show you the real world co-occurrence of these items. So when someone's experiencing an item or a symptom relating to sadness, what else are they likely to experience at the same time? And from this correlation matrix, you can then do factor analysis, which essentially reduces this space to understand the latent constructs underlying mental health. So for example, from these 4 questionnaires, we can derive 3 transdiagnostic factors, and those factors have items that either load highly onto them or lowly. So for example, we might have a dimension related to compulsivity, and on that, it would have items relating to, repeated behaviors, uncontrollable acts, intrusive thoughts. And then on it also might have low loadings for items relating to like sadness and lack of energy. And the value of this is that it, derives real world co-occurrence of items and explains them in terms of transdiagnostic dimensions. So it cuts across the boundaries that exist when we use these kind of these traditional scales in mental health. And then the value of this is that we can then look at how these are associated with individual differences in cognitive tasks and to derive the neurocomputational mechanisms underlying these dimensions. So when you're doing factor analysis, you have lots of degrees of freedom analytically, and there's lots of decisions that you need to make. So one of the first ones you need to make is how many factors do you retain? So the example I gave there is that you have 4 scales that are explained by 3 factors, but how do you get there? So what you can do is you can do something called the elbow test on a scree plot. So a scree plot just basically tells you that if you were to derive components of your data, how much variance is explained by each of those components. And the elbow test basically is the point at which the percentage of a variance flattens out by your explained components. So for example, here I would say, okay, I think at like the 3rd component is when kind of like the variance explained seems to flatten out. So I would take a 3-factor structure. This is obviously wildly subjective, so there's other more objective measures you can use. So one of them is Kaiser's rule. So Kaiser's rule basically adjusts your percentage of variance explained and expresses it in absolute values. So it's basically the same thing here on the y-axis, but Kaiser's rule cuts off eigenvalues that are less than 1. And the problem with this is that obviously if you have 100 items and your eigenvalue is 1, that's 1% of the variance, which is low. But with 10 items, once an eigenvalue of 1 is 10% of the variance. So it's dependent on the amount of items that you have. Another test you can do is parallels test. A parallels test just basically plots your actual data against simulated data, and simulated data you would assume produces eigenvalues at chance. So it's basically where your eigenvalues are below chance level. And the problem with this is when you have a lot of data, it tends to overestimate the number of factors you need. And the goal with this is always to have the smallest dimensional space. If you have 200 items, you don't want to have 200 factors. And then finally, you can use this test, Gorsuch's C&D test, which seems to be the most effective. And it basically looks at the difference in slopes between your components. So it's looking for the steepest slope point and seems to work quite well, but you need a minimum of 3 factors for it. So again, number of factors is important, but also whether or not you should rotate your data. So rotation just aids interpretation in factor analysis. So for example, say we have an X and Y axis here, and we have our items that load into space, like, these are the item level responses. All rotation does is it literally just shifts the X and Y axis in space. So these items load onto, say, this factor here more, while these items, green items down here, load onto this factor here more. So it stops cross loadings. All of these items are going to load really highly onto this factor and lowly onto this one, and vice versa for this one. The main decision you need to make when you're rotating is whether or not it should be orthogonal or oblique. Orthogonal rotations are literally at right angles to each other. So there's a theoretical assumption that your factors are not related to each other. So someone can't have a high score on one factor and a high score on another, while oblique rotation allows for the factors to be correlated. In mental health, we assume that these symptoms can co-occur. So it's very plausible that someone who has OCD also has depression, also has anxiety. So orthogonal rotations don't really apply to the mental health space, but maybe more applicable for other naturalistic data. And then finally as well, one of the big things you have to ask yourself is, okay, well, what am I going to put into my factor analysis? What's relevant? And I think one of the best examples of this is from a paper by Claire Gillen that was published in eLife in 2016, where they got 1,413 people from Amazon Mechanical Turk to complete a battery of questionnaires relating to alcoholism, apathy, depression, eating disorders, anxiety, impulsivity, OCD, schizotypy, and social anxiety. So tapping into a wide array of mental health experiences, and then did factor analysis on that. So they plotted their correlation matrix and did their CNG test and showed that a 3-factor structure was optimal and derived these 3 specific factors. So these were obliquely related. So someone who scores highly on one factor can score highly on another. But what you can see is you have this like anxious depression factor with high loading for like apathy and depression and anxiety. We have this compulsivity factor, which is high loadings for items relating to like OCD and like schizotypy. And then this social withdrawal factor, which has high loadings for social anxiety. And this kind of factor analysis in these really large data sets with lots of different mental health questionnaires has gleaned really important insights into individual differences in cognitive behavioral performance. So one example of this is individual differences in model-based planning. So model-based planning is basically the way that we generate action-outcome links and update our mental model of the world to achieve a goal. So it's very integral to like our habit system and the way that we like, navigate ourselves in the world to achieve a goal. So again, what this study did, just speaking to the Claire Gillen study again, is they got that sample to complete all these questionnaires, but in addition to that, they also did a 2-step task which taps into individual differences in model-based planning. Now, there's prior research before this showing that people with OCD tend to have deficits in model-based planning, but there was inconsistent research as to whether or not this was like specific to OCD patients only. And again, in this study, what they showed is that not only do people with OCD symptoms have worse model-based planning, but also people with eating disorders and impulsivity scores and higher alcoholism scores. But importantly, when you don't look at the individual scales and you use the transdiagnostic dimensions, you see a very specific association between compulsivity and intrusive thought and model-based planning. So this is the only factor that's associated with deficits in model-based planning, not anxious depression and not social withdrawal. And this has been replicated now, I think 6 times in independent samples. Not only that, but your transdiagnostic dimension score is more predictive of deficits in model-based planning than patient status, so whether or not you have OCD or not. This kind of factor analysis has also been really helpful for understanding individual differences in metacognition. So metacognition is your ability to monitor and appraise your cognitive experiences, and it's typically measured as confidence in your judgment. So someone who could be really correct but always rates their confidence as quite low would say to have like a negative metacognitive bias. So again, studies have gotten people to complete these batteries of questionnaires to derive their transdiagnostic scores and then looked at how this is correlated with confidence in different online tasks. And again, this is off the back of prior research being really inconsistent. So there's no consistency into whether or not people with OCD or schizophrenia or addiction problems or depression have biases in their metacognition. So some studies show positive effects and some studies show negative effects. But with this transdiagnostic approach, we see these very specific bidirectional associations where people with anxious depression have lower confidence and people with compulsivity and intrusive thought have elevated confidence. And this is something that has been shown with crowdsourced samples. We've also shown it in the lab with clinical samples of people who are seeking treatment for cognitive behavioral therapy. And it's also been replicated in even larger samples of citizen scientists who've downloaded a metacognitive game and reported their symptoms through a smartphone app. So with that, I think it's a good time to show you all like how to actually do factor analysis, and how you can actually manipulate the parameters in your model to change the dimensional space. So as Sarah said at the beginning, there's two ways you can access the OR script. If you have OR and OR Studio downloaded onto your device, you can open the workshopcode.org. And also then download the data, which is Gillen et al. elife.ords, and ideally just save it to your desktop so you don't have to change the path. Or if you don't have OR Studio, open the HTML on your web browser, and then you can also watch as I'm going through the script on Zoom. So what I'm going to do now is
just before you continue, while I make this available in the Slack again for people to access and download, can you maybe address, there's a question in the chat.
Oh, sorry.
Yeah, don't worry, just because I think it's a kind of clarification question that would be good to address now if you can.
Yeah, so there's a question just around rotations. So why would you need to rotate? So yeah, you're right, like as in you could have no rotation, and the value in rotation is that you're not manipulating the data, you're literally just shifting the axes. So the factors that you're pulling are actually just more interpretable. So with the plot that I showed, if you shifted both the axes to the right, then those blue items are only going to load onto one factor, and those green items are only going to load onto another factor. So it just means that you don't have cross loadings. It really helps with like the interpretability and the generalizability of your findings. So say it's sample specific, you might have like, certain error around like the items estimated, but when you rotate, it means that you're shifting the axes to account for that as well. So it helps with interpretability, reduces cross loadings, and also makes it more generalizable. The decision point that you need to make then is whether or not it's orthogonal or oblique. And I would suggest with mental health data that you're using oblique rotations. So yeah, I hope that answers that. I'm happy to talk about rotations more at the end. We've done some investigation into the results of different rotation types. But okay, just before I move on, then I'm just going to stop sharing, and I'm going to share what the OR script should look like. Okay. So can everyone see this?
Yes, perfect. Thank you.
Okay, great. So yeah, as I said, we'll see how this goes. Hopefully, everyone can get this up and running. Once you can input the data, there's nothing you really need to do to the code. But regardless of whether or not this works for you, this is probably a good sample code for you if you do want to do factor analysis in the future. So the first thing that I have is just kind of like the title of the script listed here. That's my authorship, and then I have the steps for the tutorial. So the first thing we're going to do is install and load packages. But before I do that, I just clear the environment. So to make sure that our environment is clean. And then I also set the scientific notations so that they're more interpretable for the p-values. So again, to install packages, there's 6 here. So tidyverse, ggplot2, polycar, psych, nfactors, and GPA rotation. So if you just highlight them and click run, I already have them installed. So I'm just going to go straight away and just make sure that they're all open by running the library. And you can check if the packages are opened by typing in the name here. So it's tidyverse, it should have a tick beside it. Again, I appreciate that there might be some issues with this. So if you have any questions or something's not working for you or you're getting certain errors, please just pop it in the chat, okay? So the next step then is once you've loaded in your packages, you're going to set your working directory. So we just have one person who says that the HTML link is not working. So yeah, I think Sarah can add in another link here to make it accessible. So after the setting your libraries, you want to import the data, and you do that by setting your working directory. So the working directory will basically just tell OR where you can find the RDS file, which has the data. So I've set mine to my desktop, so it might be handier if people just drop it in the desktop, and then the only thing they need to change is their username. So for example, if your username is Sarah Buehler, you would just change this to Sarah Buehler, and then you're going to run this line. and that should set your working directory. And then you're going to import the data, and the data should be here in the environment. So hopefully you can see that. If anyone can't, please let us know in the chat. Okay, so this data that we're importing is the data that I discussed earlier from the Gillen eLife paper, and we can look at this by hitting View Raw Data. So just to give you a sense of what this data looks like, so it's 214 variables with 1,413 individuals, and the columns in the data are like the subject, so that's the subject ID, people's age, gender, their IQ score. MBI relates to model-based planning. And then these here are like the item score. So SCZ is schizotypy score. So that's from the schizotypy scale. And if you scroll across, you can see people's scores for all the schizotypy items. If you go across again, you can see the OCI, that's OCD scores. EAT is eating disordered scores. AES is apathy scores. AUDIT is alcoholism scores. STS is depression scores. FTAI is anxiety scores. BIS is impulsivity, and LSAS is social anxiety scores. So again, with factor analysis, as I showed you, the first thing we want to do is do our correlation matrix. But in that data, we have people's like subject and their age and their gender, and we don't want to put that into our correlation matrix. We just want like the questionnaire data. So what we're going to do is we're just going to select that questionnaire data by filtering out anything that's not relevant. So all of the columns that start with the individual questionnaire like specifiers. So we run that, and then that should give us 209 variables, which corresponds with the 209 items. Okay, and then the next step is we're going to run our correlation matrix. So here we're doing a heterogeneous correlation matrix rather than a Pearson's correlation matrix. And the reason for this is because our schizotypy scale is binary, so the scores are 0 and 1. So a heterogeneous correlation matrix accounts for the fact that it's not a continuous scale. So when you run this line here, it takes about a minute to run. So while that's running, if anyone does have any questions or is stuck at any of the steps above, please put it into the chat now, and we can check it just while the correlation matrix is running. Okay, yeah, everything seems to be sorted in the chat, but if anyone does have any questions, please add them. But from now on, once you've gotten to the data part, everything should run smoothly. So yeah, while this is running, I might just kind of give you a sense of like the steps to follow. So the next thing that we're going to do is we're going to calculate the eigenvalues from the correlation matrix. So again, this is what we use to generate our scree plot. So it gives us the sense of how many components would explain variance in our data, and how much variance we can attribute to each component. So the next section is going to run all the different tests that we can do to determine the number of factors. So yeah, just as a reminder, Kaiser's rule is generates eigenvalues that are greater than 1. The parallel analysis is what we do if we want to compare our own data to the simulated data. We can do the elbow test by just eyeballing the data, but again, I wouldn't suggest it because it's highly subjective. And then the last one then that we have to run is the CNG test. Okay, so our correlation matrix is just finished. So what we'll do is we'll get our eigenvalues from the correlation matrix, which are listed in the environment, and then we can plot our correlation matrix, our scree plot here, excuse me. So again, these dots relate to the individual components. And as you can see, we have 1, 2, 3 components here. And if we were to do our elbow test, it would probably start to pivot around the 4th component and then plateau out and kind of level. So from the elbow test, we'd maybe be saying like 3 or 4 components. But either way, we'll do more objective testing. So with Kaiser's rule, we're looking for eigenvalues greater than 1. And that gives us a total of 43 components, which is quite high. But again, I said the limitation of Kaiser's rule is that with larger sample sizes, it gives greater factor numbers, so probably overestimates it. With parallel testing, then it's going to plot our own data against the simulated data and find the point where they cross. So again, this just takes a couple of seconds to run. So with this then, the limitation would be that, again, when you have a large number of variables, it tends to overestimate the factor space. And the main thing we're always trying to do with factor analysis is reduce that dimensional space to the smallest possible one, but maximize the amount of variance that we're explaining. So yeah, it's running iterations 100, which means that it's rerunning on the simulated data 100 times. So again, here's like an example of the plot that gives you the actual data against the simulated data. And this red line here is the point where it crosses over. But it will actually spit out exactly how many components you should keep. And again, it's saying 24, which is still quite a high estimate. And again, it's probably a reflection that, you know, we have 209 variables, which is quite high. And then finally, we can do the CNG test, which looks at the differences in the slopes. And the CNG test is suggesting 3. So as a first point, because it's the smallest factor solution, and that's kind of what we want, we'll go off the CNG test. So what we can do is we specify our factor number as 3. And then this here, the FA function in the psych package, is how we run our factor analysis. So the first thing you need to do, is your correlation matrix. So we'd put in H meta. We'd specify the factor number, which we've done up here, is 3. Our number of observations is the number of rows in our data. So that's 209 items. FM is the model, and we're using maximum likelihood. It's basically just a probabilistic model that our parameters like fit maximally to our data. No need to worry about it really. And then the scores are that we're taking from the regression model, so that our loadings are the correlation between the factor and the item. So this runs pretty quickly. And then FA is your output from your factor model. And what you can do is then you can extract the weights from your factor model. So again, if you think to the PowerPoints that I showed earlier, on each factor, there's certain weights that load highly and lowly onto each factor. So we extract the weights because it gives a sense of how much items are contributing to your data. So you go weights, and we're making a data frame for that. And then we can view that to see how the items load across the factors. So ML1 is factor 1, ML2 is factor 2, and ML3 is factor 3. And then these are all our items here. So what we can do is we can rearrange the order of our factors to see what items are loading really highly onto it. So with factor 1, we see STA, STAI, STS, and AES, and they all feature along the items that are really highly loaded onto factor 1. So these are items relating to like anxiety and depression and apathy. And if you want, when you're doing this yourself, you would go back to the original scale and you would look at those specific items that are loading onto that factor. And we can do the same with the second factor. So, loading really highly onto this is like OCD items, eating disorder items, some anxiety items, and some impulsivity items as well. So it speaks to more like an obsessive compulsive factor, while the first one is more related to like anxiety and depression and sadness. And then the third factor has loading specifically for the social anxiety scale, so LSAS. So it kind of speaks more to like a withdrawal item. Again, these items within schizotypy are all related to like avoidance and anhedonia. So this is obviously taken from the Gillen et al. Paper in eLife. And when they did their factor analysis, they looked at all of these items, and then they determined that the best labels to fit these factors were anxious depression, compulsivity and intrusive thought, and social withdrawal. So just for aid of interpretation, I'm going to relabel the weights now as AD, CIT, and SW. Okay, so the next thing we have done our factor analysis, we have our weights. So the next thing we want to do is actually determine the scores for each person on that factor. And you do that by multiplying their item responses by the weights on that factor. So again, that's done in this line here. So if we want scores for AD, we just multiply the weights by each individual person's data. And we do the same with CIT, and we do the same with social withdrawal. And then to get someone's score, it's just the sum of all of those multiplied weights and item responses. So again, we can create a new data frame that has everyone's scores on anxious depression, CIT, and social withdrawal, which is dimension data. And then finally, we can merge that back into our raw data frame. So if you open data frame with 3 factors, you can see that we have our subject, our age, our gender, our IQ. But then if we go to the very end of the data frame now, after all of the item scores, we have scores for each person on anxious depression, compulsivity, intrusive thought, and social withdrawal. Is that okay for everyone? Again, I can answer more questions at the end as well. There's nothing in the chat, so I'll keep going. So then the final thing that we want to do is, so we've taken our data, we factor analyzed it, we've calculated everyone's factor scores. So now we want to see how these scores are actually associated with individual differences in cognition. And again, this data has this data set has data on model-based planning, which is MBI. So first thing we'll do, we'll extract what information is relevant for our regression model. So the subject ID, model-based planning, age, gender, IQ, anxious depression, CIT, and social withdrawal. So we'll make a new data frame for that, and we'll call it MBI data. And then we're going to run a regression model to see how model-based planning is associated with anxious depression, CIT, social withdrawal, age, gender, and IQ. And the reason we put all these things in the same model is because we know that these three factors are obliquely related and they're associated with each other. So if we want to see the association between anxious depression and model-based planning, we need to account for compulsivity, intrusive thought, and social withdrawal in the model. So if we run the summary of that, it will spit out the results in the output. So you can see in the console here that this is the beta coefficient and t-value for each independent variable in our model and how it's associated with model-based planning. So also I've scaled all of the independent variables just to standardize them. So that's just like an additional step. It's not super important. It just makes them more comparable. So again, we see with anxious depression that our t-value is greater than 0.05, so it's not significant. So anxious depression is not associated with model-based planning. However, CIT is with a p-value of less than 0.001, but it's negatively associated, which means that people who have higher levels of compulsivity and intrusive thought tend to have worse model-based planning or like deficits in model-based planning. And we also see this kind of like correlation as well with social withdrawal, where actually people who have higher levels of social withdrawal tend to have higher levels of model-based planning. And then we also see associations with age, gender, and IQ. And as a final step, just to visualize this, you can plot this. So basically we can extract the information from our regression model into a data frame. And then we can label that and set the factor levels. So if you open MBI-DM, you can see what that looks like. So it's basically taken the information here and put it into a table here. And then you can use that table to plot it in ggplot. So you just run that there, and then it will kind of visualize how each independent variable is associated with model-based planning. Right. So yeah, you can just see it here. So you see you have like, there's really no association with anxious depression. CIT is negatively associated. Social withdrawal is positively associated. Age is negatively associated. Gender is males have higher levels of model-based planning, and higher IQ is associated with better model-based planning abilities. So yeah, that's kind of a very like rapid fire tutorial on how to run factor analysis on a questionnaire set, the decisions that you need to make before you run your model, and then also how to like do regression models to understand individual differences and plot them kind of like in a very basic ggplot. So yeah, the next step then is that we're going to do like breakout room exercises. And for this, it's really straightforward.
Celine, just before we move to onto the exercise, there's one question in the chat that might be good to address now by George, asking if you need to have a specific amount of variance captured from your selected factors.
So the answer is like, no, there's no like hard rule on the specific amount of variance. I think that's what like Kaiser's rule does, is that it won't accept any components that explain less than one eigenvalue, but that could coincide to any amount of variance depending on your sample size. So yeah, there's no hard rule on like the amount of variance that's explained by the components. The assumption is that as you go down, they're explaining less and less. So like a factor that's explaining maybe 0.2% of the variance isn't really contributing a lot. And you're just adding more like noise to the factor space when you're always just trying to reduce it. So I hope that answers that question. Okay. What might be nice now is if we go into breakout rooms, and with the breakout room, the goal is basically to do factor analysis yourself, but rather than a 3-factor structure, it's a 4-factor structure. So there's nothing that you actually need to modify with the code here. You just need to run it yourself, and it will produce 4-factor scores, and then it will merge that with the MBI data, and then you just have to see how each factor, ML1, ML2, ML3, ML4, is associated with model-based planning. And then there's also 4 questions that you guys can discuss in the breakout rooms. So we might allow maybe like 5 to 10 minutes for this kind of breakout room session. And yeah, I appreciate that some people maybe haven't had the opportunity to run the code themselves, but hopefully the breakout room questions are general enough that you don't need to have been able to run the code yourself. You can also see the output from the HTML. So I think everyone's been booted out of the breakout rooms now and is back in the general chat. So what I wanted to do was just go through the answers to these questions. And then in the interest of time, I might just whistle through kind of the remainder of the talk, and then that will give more opportunities for questions at the end of the session, if that's okay. So yeah, if anyone does have any questions, please feel free to put them in the chat. So what you could do is then for the first question, so what items load highest onto the 4th factor? And the answer was OCD items and impulsivity. And you did that by taking the weights, by taking like the weights data frame and then just manipulating it to like order by which has like the lowest loadings. The other thing then, the second question then was, is the 4th factor significantly associated with model-based planning? So it is. So it had a p-value less than 0.01 and had a t-value of minus 3.48. So you could get that from the summary of your regression model. As well, one of the questions related to covariates. So why would you include like age, gender, and IQ in the model? And the reason is just for account for the variance that's explained by them. So we know that they're associated with individual differences in model-based planning, and also individual differences in mental health symptoms. So we're just accounting for that when we're looking at model-based planning outcomes. And then finally as well, do you think the 3 or 4 factor is more optimal at explaining individual differences in model-based planning? So to do this, you would have to look at the summary of the 3-factor model and the summary of the 4-factor model and look at the t-values and which one is highest for deficits in model-based planning. And you could see that the second factor in the 3-factor structure, which was compulsivity and intrusive thought, had the greatest t-value for explaining deficits in model-based planning. So this kind of leads on nicely into one of the major limitations that I think there is currently in the way that people are doing computational factor modeling. So as I said, the goal is CFM is to identify neurocomputational mechanisms. And what we do is we take raw self-report data, we plot it in a correlation matrix, and we then determine the number of factors based on eigenvalues. And then the last step is we look at the associations between these factor scores and outcomes like model-based planning or metacognition. But really, the reality is at this stage, if you see any association between your transdiagnostic dimensions and individual differences in cognition, it's completely fortuitous or lucky, because you've derived these dimensions based on covariance in the item level responses, not based on individual differences in like model-based planning or metacognition. And as I just illustrated with like the script, you could have a 3-factor structure that maps onto model-based planning, but then it could be that the 4-factor structure actually explains individual differences better. And you don't know that if you're just basing things off like scree plots or, these kind of like arbitrary tests that we have. So what I've been trying to do is basically extend computational factor modeling and do it in a much more data-driven way. And we've coined the term supervised computational modeling, but the goal here is really to explore which factor solutions based on past performance covariance rather than item level response covariance have the strongest neurocognitive mappings. And we do this by manipulating the factor n. So again, not just going off our scree plot, but looking at every possible factor structure and also looking at the scales that we're putting in, looking at every possible combinations of these scales, and not just doing this in a single sample, but across lots of large independent data sets. So we've been doing this currently across 8 independent data sets with either measures of model-based planning or metacognition. So 5 of the samples have shown that those dimensions are associated with model-based planning using this like 2-step learning task where people have to learn transition rates in order to achieve a goal. But we also have another 3 samples that shown how these factors are associated with metacognitive bias using this task where you determine dot differences and then rate your confidence. And we have another sample as well that's also showing these associations between the dimensions and metacognition when people hit a particle, hit a target with a particle and then rate their confidence. So what we've done is we take all of these independent samples and we're trying to look at generating lots of different factor scores within that sample. But what we've been doing first is taking factor weights from the original Gillen eLife sample. And the reason we've been interested in this sample as our discovery sample is because it was the first sample to derive these factors. And every sample that's shown these transdiagnostic correlates since has used the weights from this sample. So what we've done is in the Gillen sample, we basically take the self-report data from the 1,400 people and factor analyzing it. But rather than just looking at a 3-factor structure, we look at a single factor structure all the way up to a 10-factor structure. And with that, you can generate 55 different factors that have the potential to predict individual differences in model-based planning rather than just 3. We've also been looking at manipulating combinations of scales. So rather than factor analyzing all of the scales together, what we've been doing is looking at each scale on its own. So alcoholism on its own, apathy on its own, depression on its own, every combinations of 2 scales. So alcoholism and apathy, alcoholism and depression, alcoholism and eating disorders, every combination of 3 scales, 4 scales, all the way up to the 9 scales combined. And if you look at all of those combinations, it gives a total of 511 combinations. And again, rather than being reliant on scree plots, what we've been doing is factor analyzing each of those combinations from a 1 to a 5-factor structure, which generates a total of 7,665 factors. So again, rather than just having 3 factors that are spit out from our factor analysis, we can get thousands of factors and see which ones optimally predict individual differences. So we test this in each individual data set by taking the weights and calculating each participant's factor score, like within each of the data sets. So again, that's what you guys did in the workshop. All you do is just calculate the sum of the item response by the weights. And you can have a participant who has, say, like a high score on factor 1, a low score on factor 2, and another participant with a low score on factor 1, a high score on factor 3. And then we do our regression models as we've done within each data set and look at the association between the factors and individual differences in metacognition or model-based planning. And again, we can compare all of the different factor structures. So kind of like what you guys did in the breakout room, comparing the 3rd and the 4th factor structure. And again, just speaking to overfitting and generalizability, we can bootstrap these t-values 100 times within each sample. And again, we can see how a 2-factor structure performs within each sample, a 3-factor structure, a 4-factor structure, and then the model would be something like this. And again, because we know these factors are related in the 2-factor structure, we would have a model with the 1st and the 2nd factor in the same model. And all of these data sets have age, gender, and IQ measured. And then finally, to determine the winning factor, we can get each independent sample that we've calculated all of these t-values for and get the weighted average across all the samples and plot them to see what t-values are the most predictive of individual differences. So when we're interested in deficits in model-based planning or underconfidence, we'd be looking at the lowest t-values. And when we're interested in overconfidence, we'd be looking at the highest positive t-value. So we've been doing this in the 8 data sets that I mentioned. I just wanted to give you kind of preliminary results with what it looks like when you manipulate the factor number. So this plot here along the x-axis represents the 55 factors that you can generate. So the first factor in a 1-factor structure, the first factor in a 2-factor structure, the second factor in a 3-factor structure, the 10th factor in a 10-factor structure. And then this here represents how the items load across all of those factors. So you can see when there's only a 1-factor structure, everything kind of loads quite highly with this dark red color. But say in the second factor in a 3-factor structure, you see negative loadings for say apathy, and then higher loadings for things like eating disorders and OCD. And these are the t-values here, how these factors, so from 1 to 55, are associated with model-based planning and metacognitive bias. So with deficits in model-based planning, the highest absolute t-value for deficits was this one here, which is the second factor in the 3-factor structure, which is CIT. So the factor that we generate using a CNG test based on covariance and item lab responses is the winning factor. Not better than none of our data-driven factors better explain individual differences in model-based planning. Similarly for overconfidence, the winning factor again was like CIT, when we get the weighted average across all of our samples. And then finally, for underconfidence, it was the first factor in a two-factor structure. So again, this is something that we generated in a more data-driven way rather than based on like, you know, the three-factor structure. But we were interested in how these two factors were related because we know that anxious depression is associated with underconfidence too. And what's interesting is that they were really similar. So the only difference between this factor here and the anxious depression factor, which we've generated historically, is that this factor just has some higher loadings on social withdrawal. But actually, when you look at individual scores, they're correlated at 0.99. So they're basically identical scores that you get from these factors. So it kind of speaks to the fact that, you know, despite generating a single to a 10-factor structure, the factor structure that you generate based on item covariance is kind of clinically sensible and cognitively meaningful. And this data-driven approach isn't doing much to improve fit. So we've also looked at then, as I said, with like combinations of scales. So specifically with model-based planning across all of these data sets, about 7% or 545 out of the 7,665 factors was significantly associated with deficits in model-based planning. We plotted the top 1,500 of them in a heat map here. And it's interesting because you can kind of see how like the best performing factors have these like really high loadings for like OCD items and like eating disordered items. And importantly, CIT is the third best performing factor. So out of the 7,665 factors, CIT, which is generated based on item covariance, is one of the top factors. And again, when we just extract the top 100, we can see that like the item loadings are very similar to CIT, and that we have these high loadings for OCD and high loadings for eating disordered symptoms and impulsivity. We've done the exact same thing with overconfidence. So again, you can see how like how many factors are associated with overconfidence in performance. We can also plot that in a heat map. And again, you see a different pattern where we see like high loadings for schizotypy items relating to unusual perceptual experiences and impulsive nonconformity. And the impulsive items seem to have high loadings, as do the OCD items. And when we extract the top 100 factors that predict overconfidence, again, like this nice pattern with schizotypy tends to emerge, which is very fitting with like the literature on schizophrenia. But we also see high loadings for impulsivity. So kind of speaks to the specificity of items that predict overconfidence. This is also true for underconfidence. So we see a much higher proportion of factors that are significantly associated with underconfidence, with anxious depression being about 1,000 out of 7,600. So again, it's still performing very well, but not as well as other factors. What's interesting about this one is that you can really see like the importance of trait anxiety across the top 1,400 factors, and these are all significantly associated with underconfidence. So we've always assumed based on anxious depression that it's a combination of anxiety and depression that predicts underconfidence. But from this, it's really emphasizing the importance of trait anxiety. And again, if you average across the top 100, trait anxiety is the kind of like items that really come true as contributing to, underconfidence in performance. So people who are correct, but when they're asked them how they're doing, they say, I'm not doing well. So again, it kind of speaks to like maybe an interesting kind of like mechanism underlying that like clinical phenotype. So just to kind of give you a wrap up, because obviously these are results that haven't been published yet, and it's still work that's ongoing in the lab. The kind of conclusions we have so far from this is that the mental health dimensions constructed from covariance and symptoms in general population are clinically sensible and cognitively meaningful. And, that's evidenced by the repeated replications of those associations with model-based planning and metacognition. And there's so many independent data sets that have shown that now. And the supervised approach that we're using beyond the natural occurrence of strongest covariance patterns has done little to fit model-based planning and overconfidence. But with overconfidence, it does seem to improve fit, specifically by emphasizing the importance of trait anxiety. So with that, the next step for us we're interested in manipulating rotation type. So I know that was a question earlier on. So for all of these analyses, we've used like the default orthogonal rotation, which is Obermann, but there's lots of different rotations that you can set. So again, another thing that's used quite frequently now in mental health research is bifactor modeling, where you have lower dimensional factors that are related to each other, and then a higher general factor. So again, looking at whether or not the rotation technique that we're using also improves fit for explaining these individual differences. So yeah, that's everything. I just want to thank you all so much, and for getting involved with the workshop, and also the breakout rooms and the coding session. And yeah, I'm very happy now to take questions for the last 15 minutes that we have.